What is the mole? A blind mammal that destroys gardens. Not that kind of mole. In this movie, to help you grasp the mole concept, we use a mind map. We imagine measuring the mass of submicroscopic particles. We speak about group words.
2,
12.
Avogadro's number.
We see that mass numbers in the periodic table are reusable, and we see how the mole solves the problems we looked at in the previous movie by linking the macroscopic and the submicroscopic. Okay, so what's a mole? Before we get to that, click on the links below for a self-marking quiz and for the mind map that we use in this episode. You can order a high-resolution poster without the watermark of this mind map, as well as the Stoichiometry workbook that it comes from on learnscience.coza. Follow on the mind map and complete the quiz to make the process more interactive. Use the timeline to easily jump to places to rewatch what you need to. Please also like and subscribe and press the bell.
Are we ever getting to what a mole is?
I'll get to a definition of what a mole is in a moment, but we're not quite ready for that yet. First, you need to understand the concepts represented in this mind map. Once you do, you'll see that the mole is the link that ties the way we practically work with macroscopic amounts of chemicals and the way we think about submicroscopic particles. The first step to understand this link is to understand another way to describe how much on the submicroscopic level. The mass of submicroscopic particles like atoms, molecules, and ions, measured in the unit AMU per atom, AMU per molecule, or AMU per ion. AMU, atomic mass units. Atomic mass units. Okie dokie. But hold on. You said atoms and molecules and ions are too light to weigh. Yes, we can't practically measure their mass. We can just think about them and pretend to measure their mass in our minds. I've never pretended to weigh something in my mind before, especially not an atom. How do I do that? Here's a representation of one atom of carbon. We know that an atom is made up of protons and neutrons in the middle, the nucleus, and then there are electrons spinning around that. We also know that basically all the mass of the atom comes from the protons and neutrons, which are collectively called nucleons. The mass of one nucleon is 1 AMU. Okay, so in my mind, I must imagine the scale going up 1 AMU every time I put 1 nucleon on it. In other words, you can count the number of nucleons, and that's the mass in AMU. Okay, yeah, that's quicker. But wait, aren't we mixing up how many and how heavy then? In this case, a count of nucleons and the mass in AMU have the same numerical value because 1 nucleon has a mass of 1 AMU. Now, how many protons does this atom have?
1, 2, 3, 4, 5, 6.
That tells us which atom it must be.
Does?
How? Well, get your periodic table and look for the element with an atomic number of 6. Atomic number is the small number, so 6. Carbon. All carbon atoms have 6 protons. The particular isotope of carbon shown here also has 6 neutrons. So how many nucleons does this isotope have?
6 protons plus 6 neutrons equals 12 nucleons.
So what's this atom's mass?
12.
12 what? 12 amu? Don't confuse that with 12 grams. Just like 12 tons and 12 ounces are not the same thing, 12 amu and 12 grams are not at all the same thing. Is 12 amu a very light or a very heavy mass? It must be light, because I can't even see that one atom under a microscope. It's too small. Yes, 12 amu is a very, very light mass. Now, look at carbon on the periodic table again. We see that its atomic mass is 12. No, it's 12.01. True, the number isn't exactly 12. That's because there are different isotopes of carbon. But let's simplify things. I agree. And let's only focus on this isotope, carbon-12. This 12 has 3 meanings. We've already referred to 2 of these. The third meaning is where we're heading with this discussion. What are these first 2 meanings? 1. How many nucleons in one atom of the carbon-12 isotope, and 2. The mass of one atom of carbon-12 in the unit amu. Now, for us to understand the crucial third meaning of this number, let's remind ourselves why we can't count how many when we practically work with chemicals, which we do on the macroscopic scale. Well, I can't go and count all the atoms inside here. Why is it impossible to count submicroscopic particles like atoms and molecules? They're too small. And there are far too many of them. So we rather weigh our chemicals. We use how heavy. Yes, but by measuring a sample's mass, we need to be able to deduce how many particles are in it. Why do we need to know how many particles are in the sample? Oh, it's that rocket problem we spoke about last time, like with the hydrogen and the oxygen in the rocket fuel. I know that I need double as many H's as O's, but I can't go and count them. So I have to weigh them. Isn't that like what we said before about taking the coins to the bank, and then the bank teller weighs them, and from that she tells us how many there are? It is indeed. But with atoms, it isn't as simple as with coins, because atoms are so tiny and light. Just when I was starting to understand. So now what are we meant to do? We need a group word. A group word? There are many group words in our everyday language, like pair, 2, dozen, 12. There are also many group words in scientific language, like kilo, 1,000. We use group words to help us to refer to useful groups quickly, to simplify our language, and to make big numbers easier. Similarly, when we have a macroscopic amount of substance, let's say this carbon, it consists of a very large number of submicroscopic particles, and we need a way to refer to this very big number of particles in a manageable way. So we use a group word to do so. Okay, but then don't we need a really big group to fit lots of atoms into the group? So altogether, there's enough that we can actually see it. Yes, true, but pair or dozen doesn't help. If we have 2 or if we have 12 atoms, we still won't be able to see them. That's why there's a special group word just for them all. Avogadro's number. Avogadro's number. Avogadro's number. Okay, so what is Avogadro's number? 6,02 times 10 to the power 23. 6, what? 6,02 times 10 to the power 23. That means we must jump that comma 23 places to the right. Gee! So that's 6,02 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 That's 602,000 million. Isn't that quite a lot? It's an enormous amount. That's how many particles there are in 1 mole of particles. Okay, so that's how many is in a mole. But who chose this number? Okay, Avagadro. Duh. But why did this Avagadro fella choose this stupid number to be a mole? Yes, indeed. Why should this particular number be given a special group name? There are infinite numbers in the number line, and only a few of them get given special group word names. Why did Avagadro choose to give this number a special group word name? It's not even a nice number, you know, like 1,000 is a nice round number to deserve to get a special name. The reason is simple. Let's go back to the periodic table and look again at carbon. Remember that its mass number 12 has 3 meanings. 2 are submicroscopic, the number of nucleons in 1 carbon atom, and the mass in AMU of 1 carbon atom. The 3rd meaning is macroscopic, the mass in grams of 1 mole of carbon atoms. 602,000 million of carbon atoms. Only if a mole is this particular number will mass numbers in the periodic table be reusable in this way on both the submicroscopic and macroscopic levels. Okay, so what you're saying is that the number 12 has a 3rd meaning. 12 grams of carbon is 1 mole. Yes, 12 grams of carbon is the mass of 1 mole of carbon atoms. 12 grams per mole is the molar mass of carbon. Here we have a mole of carbon. So how many carbon atoms are in here? Avogadro's number, which is 6,02 times 10 to the power 23. So, is a mole then only for carbon? No. These 3 meanings of the mass number on the periodic table apply to any element or any compound. Okay, how about sulfur? How does it work with sulfur? On the periodic table, we see that sulfur's mass number is 32. What does that mean? 32 nucleons. Yes. 1 atom of the most abundant sulfur isotope has 32 nucleons. So what's the mass of 1 of these atoms? 32? 32 what? 32 AMU? Now, if you could count out exactly 6,02 times 10 to the power 23 sulfur atoms, then how much sulfur would you have? A lot? Well, you would certainly have enough to be able to see. In fact, here we have them.
There are Avogadro's number of sulfur atoms in there?
Yes.
Cool!
So now we have a macroscopic amount of sulfur. How much do you guess that these 6,02 times 10 to the power 23 sulfur atoms weigh?
32?
32 what?
32 AMU.
Oops. That would be if I just had 1 atom. This is 602,000 million sulfur atoms, so 32 grams? Let me check. 32. So this number 32 is the mass of 1 atom of sulfur. Then it's an AMU. Then it's the mass of a whole mole, but then it's in grams. Cool. This number is reusable on both the submicroscopic and macroscopic levels. Wait, did you go count out 602,000 million sulfur atoms to get this all together? Well, if I had, it would have taken me many lifetimes, so no, I didn't do that. You see, Avagadro specifically chose his number so that we can just measure out the mass number in grams, and then we know that we have a mole of that substance. Okay, so you just added sulfur until the scale said 32, and then you said,
I've got a mole. I've got 602,000 million sulfur atoms.
cool. But someone must have gone and counted them out to know that you can do that. So did that Avagadro guy go and count them? Well, obviously not. Duh. Yes, Avagadro did count the number of atoms needed so that we can use the mass number in this reusable way. You said it would take
Many lifetimes, so no.
yes, if you count the normal way. But Avagadro used a very clever electrolysis experiment where he got an ammeter to count for him. Sneaky. Let's get more practice with this concept. So here's a mole of iron. Tell me everything you can about this. Okay, so I take my periodic table and I look for iron. And I look for its mass number, and it's 56. So that tells me that if I had one iron atom in the nucleus, it's got 56 nucleons. And so if I put it on a scale, an amu scale, it would say 56 amu. And then I weighed out until I got 56 grams. Then I know I have a mole. So then I know I have 602,000 million atoms of iron inside there. Cool! But why does it work out like that? Why can these numbers be reused like that? It's because a mole is 6,02 times 10 to the power 23. Why should that have anything to do with anything? The reason lies in the relationship between amu and grams. One nucleon has a mass of 1 amu. So how much do you think that 1 amu weighs in grams? 6,02 times 10 to the power 23 grams? That doesn't make any sense. 1 amu is very light, and 6,02 times 10 to the power 23 grams is very heavy, so they can't be the same thing as one another. Maybe 1 over 6,02 times 10 to the power 23 grams? Yes! 1 amu equals 1 divided by 6,02 times 10 to the power 23 grams. You said you'd give me the definition of the mole. So here it is. A mole is the amount of substance having the same number of particles as there are atoms in 12 grams of carbon-12. And how many atoms are there in 12 grams of carbon-12? 6,02 times 10 to the power 23. But why can't they just say it like that? A mole is 6,02 times 10 to the power 23. Well, that wouldn't technically be completely true, because a mole is the amount of substance that has Avogadro's number of particles. It isn't Avogadro's number itself. Okay, well, then can't we at least just say a mole is the amount of substance that has 6,02 times 10 to the power 23 particles? Well, that is what it boils down to, yes. Just check with your teacher if they'll give you all your marks if you shorten it like that. The purpose of this lesson was to help you to understand the concept of the mole. In order to understand this, it's first necessary to understand why we need the mole at all, which is that we need a link between the practical, macroscopic way of describing how much using mass in grams, with a conceptual, submicroscopic way of describing how much, using numbers of particles. The mole provides that link. A mole is the amount of matter which contains a certain number of particles, 6,02 times 10 to the power 23. Why should that provide the link between the macroscopic and the submicroscopic? For two reasons. One, because the mole is a group word which refers to so very, very many submicroscopic particles that altogether they form a macroscopic amount, so that we can both think about them conceptually and work with them practically. And two, because using this particular number for our group word allows us to reuse the mass number of the periodic table in reference to both submicroscopic and macroscopic masses, using the same number to refer to both of these, but just with different units and therefore different meanings. Okay, I get that. So you said, number one, that a mole is a group word and we need a big group of lots of atoms so that all together we can actually see the things. And then you said, number two, that Avagadro mole number thingy is special because it makes those numbers on the periodic table to be reusable so that we can use them for the mass of an atom in AMU and then the mass of a whole mole in grams. But now I'm trying to think about our rocket problem, and I'm just not sure yet how this mole thing actually helps with that. If you can't see that yet, make sure that you don't miss out on the next movie, which deals with exactly that. And you know what to do to get notifications when new movies get released. Don't forget to like and to subscribe. Finally, a reminder about the free self-marking quiz in the link below. Check how well you've understood what I've explained. We've explained, and rewatch selected sections as needed until you manage to get full marks for that quiz. Also, remember to visit the Learn Science website and the YouTube community page for fun things that you can do to get involved in as you learn science.